imagine getting an ECU and wiring it a particular way, and then getting another ECU that looks identical and plugging it into the loom and blowing it up. And wondering, why did it blow up? It's the same ECU.
Welcome along to the HPA Tuned In podcast, and on this episode we've got Scott Kuhner joining us from Australia. Scott is the founder and director of EMtron. EMtron is a brand of ECU, been around for about the last 10 years and sort of aimed more at the professional motorsport or enthusiast motorsport level as opposed to street cars. Really interesting features in these ECUs, which I think do set them apart a little bit, and in a market that is quite saturated with aftermarket ECUs. We've got a lot of choice these days. It is unusual to see manufacturers doing something that is actually quite unique. So really interesting conversation with Scott in particular around some of the key aspects that the EMtron includes, such as geofencing for functions, great for setting up particular aspects of your tune on the racetrack. Also, we talk a lot about their throttle mass flow function, which at least as far as I'm aware, not something I've seen on other brands of mainstream aftermarket ECU. Tim, from your perspective, what were your takeaways from the convo?
Yeah, I mean, obviously there was lots of really interesting technical stuff talking about ECUs and strategies and measurements and stuff like that. But I think for me, even coming into this, the thing I was most interested in was to understand how you even take on a huge project like this. This is massive.
Definitely.
Making something like this from scratch. And you know, Scott was pretty open talking about us as, you know, that they sort of pick and choose the parts that they want to be involved in as a company, and they're obviously involved with external contractors, and just talking through some of the complexities of dealing with external contractors on such a complex project and coordinating all of this and knowing what you want before you start. Maybe you don't always know exactly what you want when you start, and you just have to kind of, get
develop
a little bit
it
further down that path.
I think, the old story, which Scott alludes to as well, is when you get started on something like this, you just don't know what you don't know.
Absolutely.
But definitely daunting, giving a big bag of money to an external contractor and crossing your fingers and hoping they come through with the goods.
For sure.
Now, just relevant to our conversation today with Scott, I just wanted to talk about one of the worked examples that we put into our practical practical standalone tuning course. We've also got an Instagram on this, which is a Nissan R34 GTR. And these are a bit of a fanboy car made pretty popular by, of course, the Fast and the Furious movies. But we did a worked example on the EMtron KV8 because we were getting a lot of inquiries about EMtron content. And I wanted to give the ECU a go myself. One of the complexities with the RB26 in the GTR is that it is an engine that uses both turbocharging as well as individual throttle bodies. So that just throws a bit of a curveball in the mix there. Normally on a turbocharged engine with a single throttle body, we'd just use a conventional speed density operating system with manifold absolute pressure on our load axis for fuel and ignition. Here we use 4D mapping with both throttle position and manifold pressure taken into account. So it is a little bit more complex. And for those who do want to find out more, we do have that worked example, which will be perfect. The R34 GTR, what's your thoughts on that there, Tim?
Yeah, well, like you talked about with the individual throttle bodies there, so my understanding is you're essentially putting all of those pressure signals, one from each of the 6 throttle bodies, into a common manifold. You can then essentially average out or damp those signals out. So it's giving you some sort of reading of the manifold pressure, but presumably there's a lot going on with transients there that you're missing along the way.
Yeah, I think the key thing, because a lot of people do believe that the factory RB26 does have a little balance bar or manifold that averages all of the 6 individual throttle bodies, taking a pressure signal from behind the throttle plates. The problem that most people miss, because you can map it on manifold pressure alone, but it just does a horrible job, particularly at part throttle. And the thing that people miss is that while we're looking at the average manifold pressure, the important thing is what the pressure actually is behind that throttle plate when the intake valves are open on one cylinder. We miss that because we're averaging out the other 6. Anyway, won't go too much deeper into that. But if you are interested in learning more particularly about the EMtron ECU, that practical standalone tuning course will be perfect. Full worked example covering the HPA 10-step process. Go into detail on that 4D mapping process as well. And as an added bonus, our coupon code podcast75 will get you $75 off the purchase price of that course at the checkout. You can find that course at hpacademy.com/courses. Without any further ado, let's get into our interview today. Let's bring in our guest. All right, welcome to the podcast, Scott. Scott, EMtron ECUs, we've seen over the last few years, particularly with us attending World Time Attack, we've seen more and more cars switching over to EMtron. Obviously, we're here to discuss EMtron, the development of that ECU, but let's sort of rewind a little bit. You're also involved with Insight Motorsport, your tuning and performance vehicle business. So can you talk to us about how you got involved in the motorsport industry and how you got involved in tuning?
Yeah, well, all my life I've been sort of excited about cars. So to me, I had a Datsun Stanza that my dad bought me, 4-cylinder, naturally aspirated, not a lot of power. And I wanted to put FJ20 turbo on it. So obviously that led to engine management solutions. So I managed to pick up a ECU, and because I was already studying electrical engineering at the time, that, I was able to cross over a little bit of the knowledge, but I'd also knew how to build engines and stuff to the level you can of that as an 18-year-old.
Yeah.
And so it was just like a marriage of mechanical and electronics knowledge that led me into the engine management scene. So once I moved on from getting that up and going and working, then before too long I had a lot of friends who would be like, oh, can you tune? Oh, of course I could tune yours. And it just sort of led on, in an organic way like that. And it wasn't until that friends of mine got involved in the Australian Rally Championship in the late 90s, and we were using electronic systems, Evo Lancers, and that's what I was doing a lot of calibration, traveling Australia, calibrating those. And then, of course, I got other teams, asking me to plug in, and, there was not a lot of knowledge, even at the top level of motorsport in that. So it was very easy to get into this industry and kind of make a mark at the time. I
think it's worth mentioning that back then we didn't have access to the amount of information that's on the internet now. So you're absolutely right. There are very few people out there who actually were doing good work and getting good results. So, I saw that from my own career back then as well. If you kind of were getting better results than the norm, you sort of ended up with a flood of people at your door.
Yeah, and I was involved in designing of currency handling equipment. So we were kind of exposed to the surface mount technology at the time, and solid state, that type of thing. And I was sort of easily able to correlate that knowledge across. And, in the mechanics sort of led scene of, motorsport, that's just way above what people were at the time. But it was certainly very easy to impress people. You literally could plug the laptop in and change a couple of numbers on the screen, and they thought you were like some kind of superstar. So it was easy to impress for sure.
Yeah, unfortunately, it's a little bit harder to impress these days. Take us back.
Yeah, I've seen it, from going back to then, and people, this guy's like the best thing since sliced bread. I look back, and that person really didn't have a lot of, wouldn't survive in today's climate. However, what we did learn was very organic, and it was real world experience.
So obviously, then fast forward to Insight. So that was born out of the amount of tuning work you were doing.
Yeah, so we had Insight Services, which still exists today, which still kind of serviced, the currency handling equipment side of things, and we split off the motorsport part. And of course, I focused, 99.9% of my time on the motorsports once that got up and going. And once I got a dyno, it just sort of exploded from there. So, I'm talking 50 cars a week we were tuning. It was ridiculous. 7 days a week, all hours of the night, just in and out. And of course, you could tune a car in a much quicker time. So the ECUs we're using was always Autronic and Motec sometimes, but generally Autronic was kind of our thing. But we were doing anything, Haltech, Microtech, you name it. If it had something I can change, I would change it. And but you could calibrate an engine, to some level reasonable, in much shorter period of time than you can now, just because the subsystems, there really wasn't any back then.
So back then, when you were doing a lot of customer work with other people's ECUs, what sort of limitations or things or frustrations were you getting that presumably led you on to motivating you to go to all the trouble of building something of your own?
I'd say the first thing would be pretty much everything. I mean,
it really narrows it down.
Yeah, from an engine calibration point of view, I feel that, at the time, I would say Auditing was probably far superior to anything else from a model point of view, but it failed where none of us really know how that worked at the time, and it took a long time to understand, philosophy, so it made it difficult to get good long-term results if you didn't know what was going on. But I would say I/O would be the first thing. So I wanted to run things. I wanted, not just a thermo fan. So, in early 2000s, a thermo fan, a boost control solenoid was kind of it. I wanted to turn pumps on and off, and I wanted just to do a lot more control strategies around the vehicle, and the ECUs there just wasn't enough pins on it to do what I kind of wanted to do.
Mm-hmm. So
that would be the first reason.
It wasn't really that background, the control of the fuel and the ignition, the fundamentals of actually running the engine. That wasn't really where you saw the problems. It was the ancillary stuff that sort of went around that you wanted to expand and have more control and capability of.
Most definitely, yeah. So I was, and of course I didn't know enough to know, where the limitations were in your mapping back then either. So, you mapped the engine, or we road tuned a lot in those days before the dyno. You got the results and they ran well, and you had some limited data logging, and the mixture was good, and the thing didn't knock or whatever. And the boost controls, certainly on the Auditing at the time worked really well. It worked. It was great, but that's about all you could do with it. There wasn't really much outside of that, because even if it could do it, there's no pins on it. What are you going to do?
We're talking simpler times as well with the engine technology back then. I mean, we didn't have quad variable cam control. We didn't have drive-by-wire throttle control. It wasn't CAN communication between different electronic modules. So the actual requirements of the ECU anyway were much simpler compared to what we see today.
Oh, most certainly, yeah. I mean, that was as simple as that. I mean, the engines were, there was exactly like you say, there wasn't those extra systems that you had to calibrate. In fact, those systems will take a lot more work to calibrate than the engine, almost,
Yeah, 100%. Yeah, and I think that's a place a lot of tuners don't spend the time, and then that sort of ends up having a knock-on effect of basically affecting the rest of the calibration negatively.
Yeah, I feel that most people are in a hurry to get to that, that fuel or VE table and the ignition timing table, and that's it. They're in a hurry to get to that. And back then there wasn't much more than those tables anyway, besides a few correction tables that were provided for you. So that's all you were doing when you thought you were, tuning the vehicle.
So in terms of from the point you decided, hey, you know what, there's probably an opportunity here for us to do something ourselves, from that point to the point you actually had a functioning ECU that you could run an engine on, so what was the time frame of that?
I started thinking about doing something and kind of fiddling with small scale projects in the early 2000s. Mm-hmm. It wasn't until, I'd say, probably when the time attack scene started to come, 2007, when it was really like, okay, this is, we need to do something here. But I didn't do it from like a business point of view in my mind at the time. The sales that we're generating from a number of ECUs that we're selling was good profit. I mean, even to this day, that would be enough profit to easily sustain the business that we're trying to build at the time. So that wasn't the goal. My company, Insight at the time, made quite good income, and I had properties and things like that we invested in, and I made a decision: was I going to build a time attack car, go crazy, use it like a working hobby, or just go head first into an ECU company? If it stuffs up, well, what's the worst? It's like smashing your expensive car into the wall. That was the way I saw it from a financial point of view. That
sure.
It didn't really matter to me, the money. But what I underestimated hugely the amount of work and outsourcing, of resources that would be required to get it to the, to the point. I don't know if I would have done it knowing what I know now at the time.
That was going to be my next question. If you'd sort of had your time again, would you have gone down the same path? So
no,
maybe questionable.
Yeah, but the only problem with that mindset is I'm happy that we did it, because so much stuff that I've learned that I would have otherwise maybe gone down needed, 10 years owning an ECU company to understand. So I could easily say, oh, I'd rather just do this project than that project now. This is more exciting than ECUs now, but I needed that to get to there. Otherwise, there's no way I would have gotten to there. I would have been doing the same sort of thing.
Could you talk to what the process is for developing a product like this from scratch? You talked about having the idea and obviously the motivation to do it for your own reasons. What does it look like when you're starting something like this up from scratch? I mean, there's a lot of elements here. There's a software element, there is control strategies, there's hardware, there's manufacturing. Yeah. There's a huge number of things to pull together here.
It's the same as I see it the same as a tuning calibration. So to me, it's about building the foundation. So with a tuning calibration, it's all about getting your pin assignment correct and getting looking at your documentation, cross-checking that, making sure all the calibrations are right. It's kind of the same as with there's developing anything really, like building a race car. A lot of time should be spent on pen to paper. So getting just break it down into lots and lots and lots of little systems or little problems. Because an ECU really, if you break down like small parts of the ECU, that's not complicated. The whole big picture is very complicated. And the one problem that I struggle with, and it's very difficult to, is that, I only know so much. So you are relying on a lot of other people or other engineers or other engineering companies. And, most of our money was spent on engineering companies that I didn't know. So imagine, contracting work out, spending unbelievable amounts of money with these people only to get not what you wanted, and then having to start again when you do find someone, and because that forces you to learn more. So what we will do is we have the failed project and then learn, that didn't work. So then you kind of put a bit more, less trust, if you will, in the companies you're working with, but you do know a little bit more about what needs to happen based on that. So our path of getting there wasn't a very good path to get there, but nonetheless, it was a path.
It sounds frustrating and expensive, which is always a terrible combination. One of the things I've sort of seen from 20 odd years now in the industry, and I've lost track of how many different brands of ECU, and I'm guessing you probably were in the same situation given what you've said. You kind of find that brand A does this little feature over here, and you're like, why isn't everyone else doing it like this? This is so good. But then they do something else and it's just garbage. And then brand X over the other side or whatever, they're in the other boat. And sort of you're in this situation like, I wish I could just marry all of these functions from X, Y, and Z brand, and I'm going to have this amazing product. And I often wonder to myself, do other ECU manufacturers actually go out and test drive the competitors? And I have to say, my guess is they probably don't. Was that sort of where you came at the EMtron project from initially? Like you'd seen the best of the best and you'd seen obviously the worst that you wanted to avoid, and you wanted to bring all those features together plus your own imagination?
Most certainly. I don't think we could have gotten it to where we kind of did relatively quickly without that back-end experience of knowing, what kind of worked and what didn't. And now it's not possible to do exactly that. That's what I thought was possible. I thought, that's a good, they have a good bit of this and that function's good and that function's good. We'll just marry that together. It just doesn't work like that because it's difficult in the architecture and to generate functions that work like that, because there might be some back-end reasons why functions are a particular way they are. Okay. And it's difficult to reverse back in time, lots of hours, you go so far forward, you kind of got to keep going down that track. But I mean, for example, like even our menu system, like I was always used to Auditing where the menu would run across the top of the screen. That was my thing. And that's how EMtron, that's how I made that menu myself. I sat there literally going, okay, this is how I want it to lay out. The base architecture, even our menu system of the functions, is not too dissimilar to what it is today, a little bit more full, but it's still pretty much the same thing. But I was used to using, as in the late 2010 era, that's when we started using a lot more M800 Motex. That's in the motorsport, because the Autronic never really kept up with the CAN bus systems that were starting to come through, and some of the subsystems they didn't have available. So, a lot of the cars, we were dealing with anyway, we were running the Motec, so that kind of, that if you see, the Motec menu system of going down with your fuel ignition, that's kind of drawn a bit of that. So it's like a bit of a hybrid of an Autronic and a Motec menu, if you will, from that perspective. But we definitely did use, try to anyway, use the ideas of, the best ECUs, what I thought at the time, or the concepts.
Yeah, makes sense. I think it's often easy to overlook as well how important to the overall experience and the tunability of an ECU that user interface is. Just having something that's intuitive and makes sense versus something that's weird, and you sort of sit there wondering if the engineers ever actually tried tuning an engine using their own software. The number of times I see manufacturers get it wrong like that is quite baffling, but yeah, here we are. In terms of the development of the ECU, you sort of said, I think it was 2010 kind of started around there. We're 2021 now. Obviously, there's been a maturing of the ECU brand. It's found its feet. It's got a market out there. My question here is, obviously, the technology in the electronics world does move quite quickly. And we see generations of ECU come through, and Motec actually would be a good example here. You just mentioned the M800, that was cutting edge, and I think now that ECU is over 20 years old and is actually still going, but it's been replaced now. And again, that's not even a new ECU. Motec's M1 range was the next generation ahead. So how important is those steps in technology of the electronics and the hardware that's available to you? And you sort of, by the time you get to a point where your ECU is just about ready for public launch, you sort of look around at what's available to you and go, oh, what if I had my time again, we could do such a better job? Or is that just a natural aspect of electronics engineering anyway?
Well, the ejector drivers in our ECU came out very close towards the end of the development, when we'd already kind of been through that process. And so, we did it. There was a lot of feature creep and changes on that basis. But, of course, you can't keep up, because, the next year it's going to keep going. The next year it's going to keep going. Sooner or later, you have to make
put a line in the
decision.
Sand.
Yeah, you have to release something. So, of course, when we released the ECU, I mean, it's not even close to where it is today. However, from a hardware perspective, it's very, very much the same. It hasn't changed. Very minimal. We did one revision, which was mainly an enclosure and a packaging and some efficiency tweaks and adjustments at the time, but the fundamental ECU hasn't really changed at all. So, but when it was done, it was done without thinking of, we're going to sell this and make heaps of money out of it. Because once we got to the end of the design and, we'll do this, let's put a G-force, let's do that. Then the cost of the parts, it was made a realization, hang on a minute, this thing's costing what some ECU companies sell their product for. So that became a big problem at the time, and it was one problem we couldn't back down from. It was impossible. So we had a 4-connector ECU, 120 pins, when people were just not even thinking about that at the time, and thinking about how much I/O we wanted to have, and we kind of filled it out, 16 ejector drivers, which wasn't really a common thing at the time for sure. And then all of a sudden you've got to try and release this thing and actually generate a profit sooner or later. So I think we're lucky that at least over a handful of years that the market came to the ECU's hardware. They had no choice. I mean, if you wanted to run 3 fuel pumps in the boot, even just simple systems, like that, a couple of thermo fans and some solenoids on an automatic trans, all that sort of stuff, it would be very difficult. So it worked well that, this ECU, this EMtron ECU actually has enough I/O to do those type of things. So that did work. But ultimately, what we're doing now, there's no way we anticipated back then, when we released it, that it would need to do all of this. I mean, it was obvious that it was growing, it was going to get there, but I couldn't believe how quickly the baseline level requirement, increased.
So I'm guessing here you sort of were fortunate that you gazed into your crystal ball and looked far enough down the line and decided, look, I can see where the market's going. We think we might need this, but let's just 2x that and go here, and then all of a sudden you found that that's what the market actually needed a little bit down the track anyway?
Yeah, I actually didn't even care about the market, to be honest. I just wanted to put cool shit in it. So we're just adding so much.
Perfect business plan.
Yeah, there's literally no business plan with the fund. There was none. So we didn't do like any real form of cost analysis on production. None. I mean, we put it in CNC. My mate said, "Oh, well, I can make you a billet." Okay, cool. That sounds good. Let's do a billet case. I didn't know that. Oh, well, that's 10 times as much as what it would cost to get another one. So, and then of course we went there. I mean, years later, you could easily do a cost analysis, and you got people in the company are like, "Do we really have to have a billet?" Yes. It's like, I have got no choice but now. That's our thing. And that's actually been a bit of our branding now. So it's like, oh yeah, they have, we're kind of a bit nuts like that. Yeah. The market did come to us, but I didn't really anticipate that it would. And I didn't think it'd come to us that quickly, but it's coming to us and it's going to go past us before you know it if you stay still.
What parts of the ECU is it your own core company in charge of developing or making or designing? And what parts in general what sort of expertise would you tend to have to farm out for?
Well, I'd say that the ECU is an FPGA-based ECU. So I would say that 80% physically is done internally. The FPGA is, you could say it's a small percent, let's say less than 20% of the component of the ECU, but it's a lot. So that's one component of engineering that we've generally outsourced.
For those who maybe aren't electronics engineers, can you break down that term FPGA and give us the layman's sort of rundown on how that differs from maybe a conventional ECU that uses a micro?
I'd say the easiest way to put it's called a field programmable gate array. The easiest way to put it would be to get a bunch of ICs, I guess, put them in a bucket, and you can kind of pick them out and place them as you like. And if you don't like what you've placed, like on a breadboard, if you will, you can pull them out, chuck them back in the bucket and go grab another one. So
it gives you hardware flexibility without actually needing to change the hardware? Yeah,
correct. And for example, it has a 32-bit processor, what we refer to as a soft core inside. So that's basically embedded based in code. It's not like a big chunk of silicon sitting in there as a microprocessor. It's literally like code-generated microprocessor.
Sure.
So very powerful in that sense because you can reallocate pins and stuff like that internally.
Right. So you can take a certain pin on that chip and say do this, and then the next day it can be doing something completely different function, whether it's sensing something versus outputting something or something like that.
Imagine getting an ECU and wiring it a particular way, and then getting another ECU that looks identical and plugging it into the loom and blowing it up and wondering, why did it blow up? It's the same ECU. It's because the pin allocation could be different. So even though it looks like the same hardware, it actually really isn't in many ways. So.
And what proportion of the industry do you think would be using this FPGA approach as opposed to something more conventional?
Say you're historically motorsport-driven based, ECU companies. I would say. Higher end, I'd say most high-end ECUs would most certainly have FPGAs on them.
In terms of the development of that FPGA for your application, and again, sort of my basic understanding of this is you required some outwork to actually program that FPGA. Is that sort of a case of paying a exorbitant amount of money to an external third party, giving them a list of hopes and dreams, and then just keeping your fingers crossed that they deliver what you wanted?
Pretty much. The problem is when they do deliver it, and you can only test what to what conditions you can test under. So it's quite difficult to quantify. We spent a huge amount of time testing before we even made an engine run. Just on the FPGA part of it.
Sure.
Considering the lack of understanding inside the business, of that, but it was understood that we needed one. So we know we need one, and we don't. We obviously knew what the benefits were to us to have one, and one of which was allowed to give a lot of future proofing to the ECU with an existing hardware layout, because you could do pretty much all the things you can do in other hardware. It just would mean that you're stuck with that. That hardware, and if you want to change it, you have to redesign the hardware again.
One of the things that we quite often hear as a sort of a selling point for ECUs is the processing speed. And I've always sort of wondered, again, from a non-electronics perspective, the speed of operation of our engines relative to electronics is actually pretty painfully slow, even if you're looking at a relatively high tooth count trigger wheel. So, I mean, how important is the processing speed? Is that something we really need to factor in? And is it just a case of more is better?
No, it's a little bit like a PC. I mean, imagine if you got a brand new quad-core crazy Xeon processor PC and ran it on DOS. I mean, it's just way more than you need. So, exactly as you say, the processing power, at least fundamentally to run an engine, is nowhere near close to what people think. Faster is better. But of course, like cars, I mean, a race car, faster is better, right? So it does have an ability to do, obviously you can compute a lot more tasks in a quick time. So depending on the functions that you're trying to develop, then it will come into effect for sure. And it depends how much tasks you ask it to do as well, right? So, I mean, if you give it, a massive workload of, tasks to do, aka functions, builds, packages or whatever, then the faster the micro, the more advantageous that's going to be. Hence why, custom build packages have kind of become a thing that can be, be useful.
What sort of operations or functions from the end user's perspective tend to be intensive from a processing perspective?
Anything that does a calculation. So even a table, like a table interpolation alone is quite, it gives the ECU a lot of work. So if you have lots of tables, you're going to add a lot of processing, effort. But it's funny because, we go through auditing of processing. So we couldn't have our firmware from 5 years ago and functioning in today's and add it to the functions that we have today. There's just no way. It's just not efficiently implemented enough to just keep tacking on it. So you're kind of constantly auditing and making sure that, you can work within the ability of the hardware that you have. So, like you said, faster is better ultimately, but, you still need to be efficient, with the use of it. But it's a summing. So you have 100% of resources available. How you use those resources, it adds up. A little bit of drive-by-wire, a little bit of this, a little bit of that. But certainly complex maths, calculations, anything like that will start juicing up. But it's not like you see like a big 20% jump on your resource. It's always like 0.5% and 0.25% and 2%.
But they all add up.
And then you wonder, what's making this thing use so much? Oh, everything.
So just to go back to what you're saying there, so you've sort of got this development path, and obviously over the years, the firmware, the software gets developed further and further. You're adding new functions, and then is it at a point where you sort of have to then go back and go, this is getting a bit messy now. Let's go back and do a sort of a ground up rewrite and bring those functions back in a more processor efficient manner? Again, from my non-programming side.
Yeah, most definitely. And it's it's like auditing. It's a cleanup. It's a tidy up. If you will. But our philosophy, like today, I look at what we've got in there, and I didn't anticipate that we'd need to have kind of what we have. And there's still this huge push of, this is not that. Everyone wants it. And, we have a one release firmware, public release firmware outside of, special project contracts that we do for people. So we will write custom, firmware for a particular application for a price. And they are very efficient use of the hardware because obviously you can throw a lot of crap out that you don't need. Mm-hmm. But our process of this kind of big one-size-fits-all firmware is getting more and more difficult to manage, because the wants and requirements of people is changing so much. It's so diverse.
One of the things I was interested to come back to a little bit, what Andre was talking about before from a software perspective and certainly from a usability perspective, and as someone that represents somewhat of an end user, maybe not so much in ECUs, but definitely things like loggers and stuff like that. The quality of the software makes such an enormous difference to how I perceive the quality of the product. Whether or not it's functionally great or has great features. If it's difficult to use or it's not intuitive to use, you want to throw it in the bin, or I do, straight 100%. Away. And so how much of your effort is going into what the user's actually interacting with from the software, the UI side, the UX side, versus maybe actually dealing with the core functions of the ECU?
A huge amount. So, and unfortunately, I'm never happy. And it's not easy to get all of your wishes, because once you go down a particular path, and especially as you add complexity, I feel like a lot of my thought process now goes in, how the hell are we going to make this kind of have a high level of functionality with a low level of ridiculous complexity? And those two things fight one another. So I find that, I feel it's important to have the base, what you're spending 90% of your time on to be very intuitive and functional. To me, like with the main tunability of our system, to me, I feel so comfortable with myself. Bang, bang, bang. I'm, hotkeying away and changing and logging and pausing and doing all this kind of stuff. That might not be suitable to someone else's use to another system. But ultimately, regardless of that point, there is a very, very conscious mindset that can this thing be easy. The other problem though is there's quirky issues with everyone's software that I'm sure that you're just kind of just dealing with without even on a subconscious level. So you imagine these people who are developing this software, and because you're used to using it, you use it 10 times, even if it's a bit quirky and not really that intuitive. It becomes intuitive after you've used it 10 times in a row every day. Yeah. It's without you realizing it. So
it becomes the norm for you.
Yeah, you really do. I mean, we are getting into a situation where I feel that really you need to get, these hand pick, who's the least experienced engine management. Please go in there and change that fuel table, please. So, like by 20%. And if he can't do it, then the system's crap.
And what does that feedback look like for you guys as far as dealing with customers? You made the point where you're obviously probably the most familiar with your system, and so you're probably a pretty bad person to make a decision onto that. So how does that feedback loop look like from the end user? Is that something you guys are taking? You're actively working with people who maybe aren't as familiar with your stuff, or how does that look?
It's quite interesting because we have perceived dealer network growing. It's been growing quite rapidly over the last 2 or 3 or 4 years, and a lot of the customer base is coming from what might be perceived to be a really high-end ECU, like a very expensive high-end ECU. And then there's also a lot coming from kind of, a lower-end ECU. So you've got some kind of what you'd almost call a downgrade, if you will, in terms of cost, and then you've got an upgrade coming from people as well. So you have two ends of the spectrum, and then you have people that are kind of used to using our system. So you've got these different, like, polar opposites of people. So some are like, this thing's way too hard. How am I ever going to work this thing out? And then you have the others, oh yeah, this is easy. Oh, this is way easier than the really complicated, convoluted thing that I'm used to using. So it is difficult to trust the feedback. Obviously, you should be reviewing it, and once you get a lot of statistics of people using your stuff, you're going to get a common thread of the reports coming back. But 98% of the 2% of the users would probably drive 98% of that kind of development. So most people are happy just to use what's in front of, whether they're happy or not, but they'll just do whatever. And then
they won't tell you they're not happy.
Yeah, so there's a small percentage of the dealers that are really driving how things kind of need to be, and for better, for worse, but generally for the better.
I used to work for a motorsport software company, and I remember I was quite involved on the customer side, and I remember when I started, you would be taking suggestions from customers on everything, and you almost spent, like, most of your time was spent finding out better ways to record, track, put them in a database, whatever it is. And I remember my boss at the time was like, look, I read this book by this guy, and he said, my rule is now I never write down or record anyone's feedback. I just wait for it to sort of build up in my head, and when I know, and enough people have kind of said it to me, it'll stick in my head enough, and we'll do something about it. What's your process for dealing with feedback, either whether it's bugs, features, whatever it is?
Well, personally, I don't necessarily deal with that myself anymore. So I don't have to actively deal with that problem anymore. I see that as a problem for me.
I guess I more mean, like, from a philosophy perspective, like how you guys deal with that.
Yeah, you can't obviously don't run it as a dictatorship, and definitely don't run it as a democracy. It's probably the best way to put it, in my idea anyway. So don't just sort of, this is how it is and that's it. But definitely don't just treat it like a democracy, because for sure everyone is going to have an idea, and it's impossible to implement all their ideas and keep everyone happy. So don't bother trying to keep everyone happy. Just try to keep, the bulk of your users happy most of the time if you can.
One of the things that I've seen over the different systems that I'm involved with, obviously when we're running an engine, particularly under speed density, you're trying to model what is quite a complex situation and try and do the best job possible. And that sort of fine balance sometimes comes in of how technical do we want to make some of the functions and parameters versus how easy it's going to be for the end user. So one of the examples is, up until recently, predominantly acceleration enrichment, decel alignment was handled just based off rate of change of TPS, with some other tables around that. And I mean, conventionally, at least in my experience, that actually gets the job done pretty well. But it's kind of a band-aid for what's actually happening in the background, which is the fuel film and the effect of the fuel film based on changes in air pressure, predominantly around other things. So I've seen a lot of ECUs now jump on that bandwagon of modeling the fuel film, which is technically the more accurate way of getting the right result, but I would also argue requires a lot more input from the end user, the tuner. The other one I'll bring in, and I won't name names in terms of the ECU brand, just around getting a more accurate model of the charge temperature. And really what we're trying to do there is we want to know the air temperature of the inlet charge as it's going into the cylinder. And that's not always that easy to correlate directly to our air temperature sensor, which might be in the inlet manifold or it might be in the intake plumbing. And there was a parameter in this particular brand which basically was how much heat transfer was from the manifold into the sensor body. So basically how much was heat soak from the manifold affecting the final reading. And I mean, I guess if you look at it from a physics perspective, that makes sense. I'm sure some of that's happening, but my point there is, how the hell does the average tuner who's trying to tune a car for a few $100s or whatever, how's he going to come up with that data to calibrate that parameter accurately and get the right result? So long question, basically to bring it back and tie a little bow around it. How do you sort of balance being technically accurate and giving all of the information and parameters to do the best job of modeling versus making the ECU easy enough for the average Joe tuner to actually use?
Okay, that's a long question, but I would say, in short, that it's better to fundamentally have the engineering as best as you can, your airflow model as best as you can, and then any error you get can be by the fact that the tuner doesn't know how to offset charge. So we have the ability to correct your charge temperature based on how the airflow or how much latency vaporization is going on, all that kind of stuff. There's some the best bet there is to really, in my opinion, is to have some base values that are good, and then put up with the amount of error that you have on that basis, knowing that fundamentally in the back end that the calculation is sound, as opposed to in the history we would have like a millisecond basis where you have all these manual corrections. And like you said, it's probably easier to go in there and go, oh well, it's leaner now because it's richer now because the air's hot, let's take some fuel out. That seems easy, but it's actually more difficult. There's so many factors at play. So I'd say my best response to that is to try to have enough sensors to make the model kind of take care of itself as best as it can, such as fuel pressure, correct the fuel pressure, all those effects. And then anything that the basic level tuner doesn't understand, you're going to have error. But it's better to have a little bit of error from him not knowing than a lot of error because he has no idea what he's doing. But yes, he can go in there and manually change it. So
yeah, I think that's sort of what I've seen over the years, in particular as ECUs have become more complex with more functionality and parameters. You give a tuner who maybe doesn't have a solid understanding of what they're doing more parameters to tweak, they can get so far from the ballpark they can't even find their way back.
A simple example would be if you have, like, getting away from all that complex, air charge temp, all of that, just forget that. Just let's say the ECU is pretty good at getting you in the ballpark with that. if you don't have a fuel pressure sensor, and you sit on your dyno for a number of hours, and every car has a fuel system problem, they just don't know it. You don't have a fuel pressure sensor on it, and you tune that, you've got all your speed, all your charge temps, everything's all beautiful, just to say it's accidentally perfect. And you map that engine there, and then you come back the following morning and wonder, why the hell is this thing 1.5 points air fuel ratio richer than what it was when I mapped was perfect yesterday? I mean, you have this overheated fuel, huge fuel pressure differentiation that from what you might have had with your cold fuel setup to your hot fuel setup. And that alone is and that's getting away from just the density because the fuel's hot. Just that alone is a problem. That the fuel pressure is generally always, you'll notice, as the fuel temp starts rising, you'll watch your rail pressure it's dropping. That error there you generated is way more than probably any little, I've got it 3 degrees Celsius off on my air temperature sensor and a bit of heat soak. I feel that it's more important to have sensors that can be reliably kind of keep, really major issues in check. But that's the thing that's going to blow your engine up when you've got a fuel pressure problem when the fuel's hot and not when it's cold. That's, from my experience, that's probably a much bigger issue to address. And that's easily addressed by just turning the correction on and buying a fuel pressure sensor.
Definitely.
Sensor and putting it on.
Yeah, I think you're spot on there. I think fuel pressure is something that if you don't have the sensor, you're not actually seeing what's happening. You make some bold assumptions that unfortunately more often than not are completely incorrect.
Yeah, so I feel that that's the alarming elephant in the room. That's 90% of your calibration or engine, issues tend to generate from fuel system, changes throughout the course of the engine's operation. It can be on one dyno session to the following day at the racetrack. Who cares about 3 degrees Celsius difference on the chart? Of course it's important, but let's make the tuner not need to be so smart in that respect and try to let the model do the best job it can do and understand that, there are flaws with that. And sure, if you spend some time calibrating, of course you can make it better.
I want to get into some of the specific features that you've developed and the direction you've gone down. Just before we do that, you've mentioned CAN communication a couple of times here. You've mentioned that Auditing kind of lagged behind and didn't really follow with CAN. Obviously, as cars have become more advanced, well, in the OE world particularly, we see a lot of electronic modules, and this CAN bus is a 2-wire bus that sends messages between all of them. So particularly interfacing with a lot of the electronics in a factory vehicle, CAN communications, or an ECU that can provide CAN communications, receive and transmit those messages, is becoming more important. And even outside of interfacing with OE electronics, the aftermarket electronics world, again, CAN's become a standard for communication between dashes, PDMs, PMUs, ECUs, etc. How have you dealt with that with your EMtron brand? Again, it's one of those areas where how much flexibility do you give to the end user? Those who know how to read and write CAN templates, obviously that's really important, but a lot of people don't. So how do you deal with that?
So hardware-wise, we have 2 CAN buses, so that was kind of reasonably straightforward to future-proof the product. From an integration point of view, we kind of went down the path of what we refer to as an application build. So we would develop vehicles, CAN bus, applications that we felt were suitable for the business long term. For our aftermarket user level, we have ability to allow people to write their own templates, and it's very limited. So it's much more basic and much more simple. So that limits the functionality, sure. It also limits the support. So we actually did develop like a more complex, CAN programmable at the user level system. And there is pressure from dealers to kind of implement it. But, one of the problems with that is then you kind of just going backwards. It's very hard to backwards compatible that you're going to kind of create a huge support issue. And, say you do a firmware update and fundamentally change the way your CAN bus system works. So we kind of separated it to if someone wants something quite complex, we would just do it like a project, like a contract project. We write it for them. And of course, there's professional level people out there that have the ability to do that and might say, well, I don't want to have to pay you guys to do this thing if I can do it myself.
Sure.
But it does limit the that's kind of, again, it's a bit of a 90-10 rule. Like 90% of the people don't have a clue how CAN bus systems are, how they work and how to program them. That's changing, of course. So guys like you are teaching everyone this stuff. They're going to they're going to have more pressure on us to make that much more functional. But for certain, the level of CAN programmability in our ECU is very sufficient for connecting to PDMs and dashes and things like that, keypads and stuff. But the other way as well is we've been building up our own product base of CAN products, so that takes a lot of load off it as well, because having to make your system talk to third-party devices is very time-consuming and not very beneficial long term. But if you're making your own products, you don't really have. It takes a lot of load off that configuration side of things.
But in terms of, just to again wrap that up, basically from what I'm hearing there, if you've got your average user who maybe doesn't know how to read or write a CAN template, and they're interfacing with something pretty conventional like a PDM or a dash, that's as simple as just enabling communications inside of the ECU, and the job's done. Putting a
default data set with a few base settings, and our support team, they have like some templates for most commonly used dashes that they can load in. And the dash manufacturers most of them have got an EMtron set, for example, in them that they just configure up to our base template, our predefined template. I never use that, of course. I don't use predefined much, but you just write your own custom set if you want to be a little bit more creative. But it's not as it's not at a programming level of capability we haven't provided for.
Yep. All right, so let's talk about some of the features that you wanted to do differently. And I mean, on face value, obviously you're here 10 plus years after you decided to come up with this idea, but on face value back then, you could argue it might have maybe sounded a little bit arrogant with the number of aftermarket ECUs that were out there and still are, to be able to sort of develop something and do it bigger and better than what was already on the market. And I just really want to dive into some of those unique functions that, or maybe not even unique, just the stance you've taken on the way your ECU works. So in terms of the functions that are key, one of the ones that you've got there we've talked about is torque-based or torque modeling. So can you talk to us about what that is, how that differs from a conventional fuel model?
So the torque modeling kind of was born out of requirement to do more vehicle integration with factory vehicles. So a lot of the Bosch Euros, the Japanese R35 GTR is one of the biggest projects that we've done at the time. We soon realised that, so we had a normal VD-based system and lots of ignition and retard and cutting capabilities with all of our motorsport functions, which is what I wanted to do, obviously, when we started. But what I soon realised was very difficult to integrate it with the factory seamlessly, because so many subsystems coming in and requesting. So what I didn't understand was, early in yes, I wanted more boost tables. I wanted more of this. We want more traction type of feed-forward inputs to make the traction model better launch control strategies, more ability to change it on the fly, all that kind of stuff, making kind of existing functions that are around just better and more powerful and do more with them. But what you soon realise is that it's very difficult to have, say, 10 subsystems all trying to cut and retard, change gears, paddle shift, downshift, do subtractive control, retard the timing while the nitrous, all that kind of stuff. And so we had to build a much more accurate torque model. So we had a very basic torque model. You couldn't really even call it a torque model, to be honest. But now we've put a lot more effort into the torque model. And the reason being is that an OEM manufacturer, nearly every function, is requesting some kind of a torque. So the subsystem will come in and say, hey, ECU, please can you drop, I'm going to change gears now, so please take 200 newton meters out. And you say, okay, cool. How do you tell an ECU how does ECU take 200 newton meters out? Of course you can cut fuel, you can cut spark, you can retard and all that sort of stuff. But how do you know how much to do that to get that torque? And then the main thing around torque reduction is how do you close the throttle, which is available to you? How do you close the throttle? And how much by? It's easy, just okay, cool. We want let's close the throttle. That's easy. But how do you know how much to close the throttle? Rev matching is a simple example. Most rev matching will open the plate to a particular position for a period of time, and maybe do some cutting or something. And as you downshift, and the dog will engage, but the rev is kind of matched like you would with your foot. What do you do with an R35 with dual clutch? where you have to rev match, but you need to constantly rev match and achieve a particular level of throttle plate to achieve that exact right amount of RPM, whilst you don't know when it's going to go into gear. So you're waiting and waiting and waiting, and then the gear engages by the TCM, for example. So if you can't accurately calculate the torque that the engine's producing, it's pretty well impossible to get good results. It's not impossible to get results, but it's impossible to get good results.
Sure. What's the approach there with when you're talking about the torque modeling? Is this based on modeling physical properties, like modeling, like for argument's sake, like something like modeling the flow with something like a CFD model, and it's actually based on physics? Or is this based on empirical data? A throttle body of this size at this mass flow, you've got to get an empirical model fitted to it rather than being a physical model?
I'd say a combination of both. Yeah, you could do it just a pure science, but it is a combination of empirical data. A bit more than that. I would say it's a small percentage of empirical data. That's probably enough to calibrate your torque model. Mm-hmm. But ultimately, at least the way we do it is with a throttle plate, is looking at a pressure difference of the throttle, and factors of throttle area go into the calculation. Torque modeling with throttle is usually can become quite accurate at pressure ratios a lot less than 1. In other words, the pressure is a lot different. So from before the throttle to after the throttle, that calculation works very well for when you're torque reducing based on closing the throttle. If it's asking you, please close my throttle, I want 200 newton meters of torque. Okay, bang, and the ECU will just go there naturally, and not kind of like what people may think, and what I kind of originally was thinking was that maybe you would just close it until the torque that you've calculated from some airflow model. It can't work like that. It literally needs to go to a calculated value.
So it needs to predict where it needs to go to, as opposed to updating in a loop.
Yeah, you'll be way behind. You'll never get there. You'll just be like, oops, I'm late. So you need to calculate where it should go, and it needs to go there. All those systems that require torque, modeling or requests, just quite simply won't work. Where it gets more difficult is that you close the throttle and then you say, okay, well, I want to cut as well. Then all of a sudden you've got less torque again, right? Or I'm retarding and I'm cutting. But, but of course, when you're cutting, you're not retarding that cylinder because it's cut.
What about when it comes to doing something like rev matching, like you talked about before? Is it a situation where you're modeling like the inertia of the engine? Or again, does it come a bit more
we aren't using inertia. Well, we are, but we're not necessarily calculating inertia to kind of put that into the model. You could do. You could be. One of the main contributing factors is a frictional loss. So as the higher the engine RPM for a given engine, you'll get a lot more friction. So that needs to be factored into your model for torque. But ultimately, just in a simple way, imagine if you said, I want to achieve 6,000 RPM for a given engine. I'm going to open my throttle to achieve a net gain of 0 newton meters. The engine's producing, give or take, close enough to around 0 newton meters. And the engine won't be accelerating or decelerating. So imagine if you have the engine and take away the effects of inertia, and you rev the engine on the spot to 7,000 RPM. Okay, so it's taking a certain amount of torque to get to 7,000 RPM, but you're in neutral, you're sitting there. There's not a lot of work, there's not a lot of torque getting produced, at the flywheel, if you will, but there's a lot of airflow, there's a lot of torque getting used to get the engine to there. When you take your foot off the throttle, the friction starts overcoming this, the engine, and the engine decelerates. Hence, you are achieving a negative torque. If the engine's accelerating, you're kind of creating a more positive torque. So a lot of the torque modeling and launch control strategies, which we use exactly the same concept, if you will, is about trying to maintain, a torque that doesn't increase engine speed or reduce engine speed, and that's how you can perform the rev match. So I can calculate very easily in the back end where, okay, I want to rev the engine to 7,000 RPM. And of course, you've got all the different factors at play. Like on a 35 GTR, you've got these turbos, and they're spinning faster or slower, so the pressure may be different under different circumstances. So you can't just put a blanket, okay, 30% throttle is that much RPM, for example. It's not going to work like that. You need to know the pressure difference before and after the plate, factor that into the model. But that's, I mean, it's very, very simple, from the outside, but in turn it's very difficult to come up with those, those calculations. So, lots of fun.
Just in terms of one of the things you've mentioned there, just in a torque reduction. So we'll use this for a gear shift, for example, and you brought up the DCT example. So you've got a variety of techniques that you're in your arsenal, depending on exactly how much torque you want to reduce. And you've talked about that. We can retard the timing. We can cut fuel or spark to a cylinder or multiple cylinders. We can close the throttle, or we can do a combination of all of those. So what's the logic there based on a requested torque reduction? How does the EMtron decide which of those tools in its tool belt it's going to employ?
There's two ways, really. One way would be to do what the OEM asked us to do. So, on a 35 GTR, if you do a gear shift, it will say, please ECU, can you retard my timing and close my throttle? And I want this much torque reduction based on the throttle closing, and I want this much torque reduction based on the retard. Then the VDC might come in, so the stability system, and it will say, hey, I want some torque reduction. I want this much torque reduction due to cut, and I want this much due to closing the throttle as well, for example.
Sure.
So they'll be separate requests. In our functions, we write functions with the ability of the user to dictate what it does. So, for example, drag car launch control using torque. You essentially a big pro turbo clutchless style cars. They need a lot of turbos. They've got huge turbos, and you need to get that engine to sit at 7,000 RPM or 65 or 7,500 RPM, and it needs to stay there quite consistently to make sure the clutch characteristics stay the same because of the slider clutches and so forth. So what you will need to do is say, okay, ECU, please give me 7,000 RPM. So the ECU will go away and say, okay, cool, we need to have roughly 0 Newton meters of torque at 7,000 RPM. But I'm retarding, right? So I want to spool. So if you tell the ECU to prioritize retard, it will hold the engine speed just based on retard only, for example. Of course, that will spin the turbo up quite quickly, but then you run into issues of heat, depending on how much you retard. But so then you may have to kind of revert to a cutting strategy, and you can let it decide on the fly. You can do the same thing with cutting or closing the throttle. What the ECU needs to do then is when it's cutting, it needs to say, okay, cool, well, we're retarding here. We've got minus 20 degrees in the engine. All right, we're going to cut now. It's like, okay, well, we actually better reduce the retard to maintain that same torque because cutting is another factor at play now. So the ECU needs to calculate that on the fly. That yields extremely good boost response on drag car, maintaining good RPM, because I guess you know that playing with drag cars, you have large turbo drag cars, and you're always kind of tend to be juggling around how much retard and how much cutting, when the range of cut, and I retarded too early. So the ECU takes care of all of that for you, provided the model is set up correctly.
So on face value, that sounds like it makes the tuner's job a little bit easier. What I wanted to get back to was the torque model that we've just talked about. It does sound pretty complex. How much more workload does that put on the tuner compared to a conventional volumetric efficiency based model? How many more parameters need to be calibrated, or is this predominantly your modeling in the background that's doing the heavy lifting?
I'd say it puts a lot more load on the person who is building the base calibration.
Okay.
So I wouldn't necessarily say the tuning person, so the person there on the dyno, but assuming that's the same person, it will put more load on the person building the calibration before the wheel turns. The problem you'll run into is if you don't put any work into that, it's worse than just cutting and retarding and doing the normal thing. So first step is to make sure that calibration is done well. If you can get those factors, throttle body sizing all dialed in well, a lot of the base behavior, the frictional loss numbers, and I mean we provide base numbers, and I almost guess them now. You do so many engines, you understand roughly what kind of friction numbers you should be expecting to see and stuff. But once you've done that, your functions that are relying on the torque modeling, and our ECU is kind of a hybrid at the moment, so it's build up of more is better. It's more table, build more. That's how it was. Now it's kind of becoming a hybrid because we're like, well, that's just too hard. I mean, I don't want to be sitting there working out how many degrees of timing, how much cut percentage I want to do here while the gear's shifting, and now I've got to do a torque reduction. It's just a disaster. So that now becomes so much easier when you just torque model it, and the ECU knows all the time, how much torque reduction is going on. So if one subsystem say, hey, I want to pull some torque out here, and the other one says, well, I need this much out. Well, you go, okay, cool. Well, I'm already asking for this much out, so the ECU just will do the demand. So more of the job becomes on prioritising what torque reduction or not reduction should and when it should occur. So if you're doing a gear shift and the rev limit is happening, what's trying to take priority here? So what torque request, if you will, is taking priority. Yep. But long term, much easier to do complex functions.
Sure.
Definitely.
I'm guessing as well, as you develop more and more base packages for common engines, you're kind of doing that heavy lifting for the end user and doing all of that hard work that they may not be capable of. So from their perspective then, unless they've made really dramatic changes to that engine package, it does just become tuning as normal?
Definitely. And I mean, we've left legacy functions in the ECU kind of for that reason, to kind of like, break the fall, if you will, to make sure that, people can say, okay, well, I just want to go and cut this or retard that. Okay, well, you can go and do that. Long term, as the education increases and the functionality becomes more core to a torque model, then, that would inevitably disappear for certain in the long term.
The other thing, you've kind of alluded to it here, throttle mass flow. So this is something that I've tried to pin you down at World Time Attack to talk about on camera a couple of times. You keep running away from me, so we got you stuck now. So this is something, to the best of my knowledge, I haven't heard of any other manufacturers really dealing with. So can you talk to us about what throttle mass flow is and why that is important compared to just a conventional speed density system where we're just looking at manifold absolute pressure in the plenum chamber?
Well, in short, outside the concept of just thinking about torque strategies, let's just talk about airflow and how accurately, I guess in my opinion, that what you're doing with the speed density, I guess maybe it's not an opinion, it's that, you are trying to estimate the air mass. What's going in the cylinder. So this is just another way to estimate the air mass. It's using a number of sensors. It's more complicated than just putting a manifold pressure sensor. But a simple example would be, imagine if you have a large throttle body and a small engine, and you are doing some low RPM, 1500 RPM, and you're pulling a certain amount of manifold vacuum. As soon as you crack that throttle, you'll vacuum the manifold, you end up with like 100 kPa, so 100% load, let's just say. But of course, you might have another 60 or 70% of throttle plate and increased airflow going on that the manifold pressure sensor doesn't see. So the problem lies in that circumstance is the accuracy of the airflow model is terrible under those environments. Now, a lot of people don't really realise this. A simple test for the viewers would be, if you get a car and let's just say it could run a bar of boost and you do a power run at full throttle, go do that same power run at the least amount of throttle required to do a bar of boost and tell me how good speed density is. You'll come back and tell me that, why is this?
It'll be running rich. Yeah,
100%. So the throttle mass flow, it is very accurate at calculation of looking at when you have a pressure sensor before the throttle, you have a pressure sensor after the throttle area. It is very, very accurate at generating an estimate, an airflow estimate, in a high pressure difference environment, hence when the throttle is closed.
Sure.
So we inadvertently kind of I'd say stumbled onto, wow, this thing's quite cool. I was almost joking with myself, but let's just try and tune the engine on this model a bit. It wasn't designed for that. It was designed to try to generate an accurate torque to the engine. But then it made sense. Obviously, if you try to generate an accurate torque, then it makes sense that it's probably good at generating an accurate airflow. So in a reverse manner. So I started sort of calibrating and noticing that, when the pressure ratio is 1, let's say the throttle's open, the pressure before and after is the same, I started noticing this thing's spitting out ridiculous crap data because it relies on a pressure difference across the plate to generate accurate results. So, but that's cool because the speed density lo and behold, is brilliant when you have a throttle completely open, and the manifold pressure is what I would deem to be extremely trustworthy.
So you've got a hybrid system that switches between throttle mass flow and conventional speed density based on that pressure ratio across the throttle butterfly.
Exactly. So when you have lots of closed throttle, whereas an engine spends 98% of its life, generally, even a race car spends a lot of time in a closed throttle environment, you can generate much more accurate estimates of airflow than what you otherwise could with speed density, basic manifold pressure speed density system. So, but you have the added benefit where you can sort of blend into or transition, or however you like to put it, into a speed density that we all know and love, and it's very reliable, and it gets out of the issues of mass airflow meters, which obviously extremely accurate throughout the whole range of use. But so this is kind of like giving you a bit of the best of both worlds of accurate airflow measurement at low throttle areas and accurate airflow measurements at high throttle areas. It puts a little bit more load on the user, of course, because you're kind of calibrating two systems as opposed to one table.
Yeah, I mean, I think anyone who's spent any time on a dyno with a turbocharged engine will have seen that phenomenon where everything's absolutely beautiful at wide open throttle, but the turbo is so good at making boost that you can close that throttle at, let's say, 5,000 RPM in one bar. You might be able to close the throttle down to 40% before you really start seeing an appreciable drop from that one bar of boost. So, of course, if that's your reference point, one bar boost, 5,000 RPM, let's say, that's what the ECU is seeing. But of course, as you mentioned, the airflow is quite different at 40% throttle. So that's where you see that rich phenomenon. So yeah, it's just interesting to sort of get a perspective on how that throttle mass flow works.
Yeah.
Moving on. Sorry, go on.
Yeah, like I said, and it's an accident. It was an accident that we kind of stumbled onto that, for sure.
No, it's probably a good accident to have. Moving on, another one that I wanted to mention is probably like a little bit more left field. And again, I haven't really seen much of this being done elsewhere. Geofencing. And you're using this based on GPS coordinates with some of your racetrack applications. So can you talk to us about what that is, how it works, and what you would use it to control, for example?
So generally what you might do, I mean, my experience is time attack with that kind of side of things. But you're essentially sectoring up your track, and then you are like into corners and straights, and then you're managing to use, change the engine's characteristics, or you can maybe turn different systems on and off based on those segments of the track. So nitrous is a good example where, the nitrous can be unsettling on the car. So you might decide that, well, all the conditions being equal, it should not turn on it, turn to at Eastern Creek if anyone knows Eastern Creek Raceway. So, track. So that's one example of the use for it. It's something that we've been doing for quite a long time. It's been reasonably effective. We're kind of moving away, mindset-wise to that, to try to make the ECU be a little bit more smarter, in real time, and kind of sort of telling it, hey, ECU, do this at the spot of the track and don't do it at that spot of the track.
There's another way we could go about that as well. So geofencing using GPS, obviously that makes sense. There's a bit of work, I guess, in setting up those parameters on whereabouts on the track you want those GPS coordinates. Instead of doing that, using basically distance from the start-finish line, which basically all of the logging systems that you use GPS timing will generate. In your opinion, advantages of geofencing over just track distance for turning on functions?
Well, at least for if you're doing a GPS coordinate, if you will, that's going to be a bit more stable and not having to worry about, beacon issues associated with start-finish line. So you can have pit lanes that are close to the start-finish line. So it can be a little bit difficult. So you are right it's right. So yeah, okay, well, we could just reference everything from the start-finish line. But if you just have, literally a GPS coordinate that says, hey, this umbrella of area, you can do this. This is now becomes a sector. But, like I said, I just don't, now my focus is more, that feels more to me like a bit more of a patch over just having the car being a bit smarter in the environment. The problem is that we didn't have sensors that could read all sorts of vehicle dynamics at the time. So, we had a G sensor, X, Y, Z G sensors. Now you have a lot more data available that you can leverage and, make decisions based on that. But certainly it's still valid, and we still do commonly use, similar concepts like that. But my personal, drive is to try to just make the car be smarter somehow. Easier said than done. You commonly spend a lot of time playing around with,
get the basics right rather than adding multiple band-aids on the top to get the end result.
Exactly, yeah. Kind of let it try to take care of itself. So that's proven not that easy. Of course, there's so many factors at play. We used to, we've been around tuning engines for years. It's an engine, and now we're trying to tune the whole vehicle with the same thing. So it's become a lot more challenging to try to generate results with all that data.
Right, I think we're going a little long here, Scott. So I think we'll start sort of heading towards a bit of a wrap up and let you get back to making ECUs or whatever you're up to today. Yeah. But before we do wrap up, is there any other sort of cool features, new functionality that you've kind of got on the design board at the moment that you'd like us to know about?
Well, definitely we're working on our direct injection solutions. So that's going to have, just like all of our other products, lots of voltage, lots of current, lots of grunt, lots of power. So hopefully that can sort of put us into the future another few years with up and coming sort of engine technology. So that's one project. We're putting more efforts into data acquisition, and we are putting pretty much our full effort into making sure that we can build a full suite of EMtron products to support motorsport, as opposed to kind of marrying it up with some of the other products on the market. That's going to be a bit slow at the moment because there's a world semiconductor shortage at the moment, so anything that we do develop is going to take probably a hell of a lot longer than what it otherwise would have in terms of prototype turnover. But it is exciting nonetheless, and we pretty much, if you can think about it being used in motorsport and it's electronic, we're going to look to develop.
One of the questions we like to ask on the podcast is if the guest has any advice for maybe a younger version of themselves, if they're going to follow a similar path, or maybe for other listeners that are listening out there and are interested in following a similar path. And I think from your perspective, from coming from the perspective of building, a product of your own from scratch as well, what sort of advice would you have for someone that was interested in taking on a project, whether it's an ECU or anything electronic or not?
I'd say, I don't know if I'd call it advice, but I'd call it what worked well for me was don't listen to my mum on the basis of that she wanted me to just do a 9-to-5 job for the rest of my life and then a stable $30,000 salary. So in that respect, it might have worked well for them, but it didn't work for me. Don't think about money. Just don't worry about it. Like, as long as you got food and like if you have children or whatever, or let's just say my age back then, you didn't have children or dependents, don't worry about money. Just do it. Like, just do it. As long as you've got the means to survive, I just don't worry about that kind of stuff. Like, even today, of course there's financial worries, but it kills creativity. Like, if you're just constantly thinking about money, it's just going to kill engineering. It's
a good point. I think if you've got a product that's maybe been designed and built by an accountant, it's going to be stifled down a little bit compared to what you've obviously created, as you've said, without a business plan. Yeah. But I think it's fair to say as well, if you're building quality products just about in any industry where you've created something with a real genuine market, in most instances, the money will come. So I think the passion for the product and building quality definitely trumps trying to do something just to make a buck every time, regardless of what that may be.
Yeah, and probably my other piece of advice is don't think you are the best. Like, just think you're dumb. I mean, I constantly get surprised by what I don't know. So don't think you're the greatest thing since sliced bread. Spend no time telling anyone how good you are. Just do it. Like, learn. Like, you have to do that. You can't be just sitting on social media platforms all day telling everyone how good you are, because that's not going to make you any better. Just do a lot of reading, read books, do your courses. That's we didn't have those back then, so it wasn't as easy as it is now. So
I didn't have them back then either. Yeah, I think it's the Dunning-Kruger effect. I think as you start to build a little bit of experience, you suddenly think you're a genius. And for us who have maybe been in the industry a bit longer, you sort of start to realize that the more you learn, the more you don't know. Which, for me at least, is why I still am passionate about the industry 20 years in, because there is always something new to learn, and I'll never stop. But I think a lot of people, maybe 1 or 2 years in with a few successes under their belt, think that they know everything and that's it, they can kick back, and it's just not the case.
Definitely not the case. It's for sure. And get yourself a good hobby outside of this too. Like, I probably didn't do enough of that, but I'm definitely now trying to do more of that. Otherwise, your brain just goes fried.
Last question for today. If people want to follow you on social media, or EMtron for that matter, where can they find you?
We have a page on Facebook. I'm not sure what it's called, but it's
probably EMtron something or other.
Our website's emtron.world. So yeah, all the details will be available there.
I'm gonna assume that our listeners are probably smart enough to be able to use Google.
I'd like to hope so.
Thanks heaps for your time today, Scott. It's been really interesting.
Yeah, thanks,
cheers, guys. Thank you.
Thank you. Cheers.
All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school, and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.
Nice.
Got there in the end.